Hi, it's me, Tim Dodd, the Everyday Astronaut. Welcome to Starbase, Texas.
Today, we're getting up close and personal with SpaceX's Raptor 2 engine with Elon Musk. We get into all sorts of details on this engine, including how exactly it's been upgraded and simplified compared to Raptor 1. This video has a ton of fun details on some fairly technical stuff. So be sure and watch my Why Don't Rocket Engines Melt video so you know what we're talking about with some of the cooling techniques, as well as my video on engine cycles, so you understand how the Raptor's full flow stage combustion cycle works and why it's advantageous. My next video will be a deep dive comparing Raptor 1 and Raptor 2. We'll go over every little detail of the engine, and it'll definitely help make this conversation easier to follow. It's currently in the works, so be sure and stay tuned. If you happen to find this video valuable, consider dropping a super thanks as a tip below here on YouTube, or become a channel member or Patreon supporter for early access and to show your support. Okay, let's dive into SpaceX's Raptor engine.
So these were all Raptor 2s.
These are all Raptor 2s?
Yeah.
You have this many here already?
Sorry?
You have this many here already?
Yeah.
In my head, I just wasn't even thinking. I mean, yeah, they're a lot simpler. Oh, you can see that kind of octave valve thing on it.
Yes. So there's one, the Raptor 1 is the one that looks like the crazy Christmas tree there.
Hence the Merry Christmas.
Yeah. So
And a snowman.
it's not super easy to see, but you can compare like how much less there is. Like if you just look at just eyeball the fiddly bits level there versus the fiddly bits level there, like that thing's just wrapped in tons of stuff.
Yeah.
This is a completed engine.
Wow.
So a massive amount of things have been deleted. Deleted, combined, simplified on Raptor 2 versus Raptor 1. It's a little hard to see because it's over there, but
You can tell a lot.
yeah, giant difference. Like this, the Raptor 2 looks like it's not finished.
Yeah.
But it actually is. This is a finished Raptor 2 versus finished Raptor 1. Gigantic difference.
And you can tell this one's a lot more completed with the gimbal mount on top and everything too.
Yeah. Well, that's good. They both have a gimbal mount.
I mean, sorry, compared to like that one that doesn't.
Yeah. So the outer booster engines don't need a gimbal.
Right.
So the booster engines are fixed, as are the Raptor vacuum engines. But this is a gimbling Raptor 2 versus a gimbling Raptor 1. Gigantic difference in complexity, and this is the Raptor 1 was really around sort of 185 tons of thrust, and Raptor 2 is 230 tons of thrust. But really, I think we can probably get over time 250 tons of thrust. So it's
230 tons at
sea level.
300 bar?
At 300 bar.
Wow. And you've been pushing these things to like over 300 too, right?
Yeah, so Raptor 1 could maybe do like 250 bar, and it also has a smaller throat.
Yep.
So whereas Raptor 2, a standard operating pressure is 300 bar, which is this is crazy for a rocket engine.
Yes.
Where it have a main chamber this is by far a record.
Yes.
300 bar main chamber operating pressure is it's the highest pressure operational rocket engine ever.
Yeah.
So the next best would be like a RD 180. I think they're around 267 bar, thereabouts.
And you're already 170 is not too bad itself, but it's it's. I finally.
No one's ever done 300 bar.
No, especially not sustained. I'm sure they did it on, maybe blew one up and trying to get there or something.
Oh, we blew a lot of engines up.
Yeah.
I've lost count of how many. I think we might have blown up 30 engines, or that's a lot.
Yeah.
That's why like a high production rate cures many ills.
Yeah.
So if you have a low production rate, like I mean any given technology development is how many iterations do you have, and what's your time and progress between iterations. So if you have a high production rate, you can have a lot of iterations. You can try lots of different things, and it's okay if you blow up an engine because you've got a high production rate. You've got a bunch of engines coming after that.
Yeah.
If you have a small number of engines, then you have to be much more conservative because you can't risk blowing them up.
Yep.
So that's why, one of my catchphrases is a high production rate solves many ills.
Yeah.
So we've blown up, I don't know, I'm just guessing at least 20, maybe over 30 engines, and we have melted probably 50 chambers, maybe more than 50 chambers we've melted.
So when you melt the chamber, are you most of the time able to like save the power pack on it, or do you just have to scrap the whole thing?
If you melt the chamber, it's usually a benign shutdown. So you've lost the chamber, the sort of chamber nozzle assembly, but the pumps are usually fine, and you can potentially even reuse the main ejector.
Okay.
But basically everything below main ejector is toast.
Is it potentially benign because as it erodes the layer, it actually begins to almost cool itself more?
Yeah, it's benign. It's like benign in the context of rocket engines.
Yeah.
So
until it starves the injector and creates a hot spot, I'm sure, and all that kind of stuff.
So I mean, if you don't shut the engine down fast, you will have an explosion.
Yes.
But you do have an opportunity to shut the engine down because you can detect a big pressure drop in the the chamber jacket pressure will suddenly drop.
Right.
And then you can do a commanded shutdown of the engine. But you will have issues if you don't shut it down because the cooling fluid, the fuel that is cooling, is now no longer cooling the part above it.
Oh, right. Yeah.
So it's cooling where the leak is, but it's now doing less cooling of whatever's above it.
Right.
So it's going to start melting all the way up.
Gotcha.
So it'll get ugly fast if you don't shut down.
And so that you mentioned at the last Star Trek event, you were kind of saying, yeah, Raptor 2s are melting. What have you ended up like? How do you keep them from melting? What tricks are you continuing to employ and expand out on, or is it just a matter of tuning the engine back a little bit even to not be pushing it that hard, or?
Well, right now we're optimizing Raptor 2 for robustness as opposed to performance. I think broad brushstroke, we're kind of overdoing it on the foam cooling front.
Yeah.
So we have quite a high percentage of head end foam cooling and throat foam cooling.
Yep.
So this, we're probably losing a couple points of efficiency because of the cooling, but it's better to have not melting chambers, and we can fine tune the performance later.
Yeah.
So we're just hitting cooling with a sledgehammer here. So some pretty significant improvements for Raptor. I'd like to compare Raptor 2 to Raptor 1. For Raptor 1, we have torch igniters in the main chamber. So you can see that the torch, those things on the side there are the torch igniters. I mean, these guys basically. So you got torch igniters for the main chamber. But Raptor 2 has no torch igniters in the main chamber. So you can see it's much cleaner around the chamber area.
How's it light then?
Well, that's a secret sauce. But I'm just, I can tell you sort of observable outcomes that anyone with a camera could notice, but I cannot tell you secret sauce things. Anyone can see what the outside of the engine looks like because we have to trundle the engines down the road, and people have, 12K cameras with telephoto lenses that are so precise they can read the serial numbers on the wiring, literally. So I'm not giving away anything, any state secrets, literally, by describing things on the outside. But I have to be cautious about saying how we made it work.
Gotcha. Yep.
But it wasn't super easy. But we managed to get rid of the torch igniters in the main chamber, which is significant complexity reduction and reduction in failure modes. Makes the engine lighter, lower cost.
More reliable on ignition and things like that too?
Yeah, wow. Exactly. So it's better in every way. It was a huge improvement to get rid of torch igniters in the main chamber. We still have torch igniters for the oxygen power head and the fuel power head, but we were able to simplify those as well.
Because that's something that would sometimes cause scrubs. Even it'd be like a pre-burner itself won't even light. Yeah,
if the pre-burner doesn't light or even doesn't light exactly right, then you've got a challenge. So with the Merlin engine, you've got a single shaft that is driving the oxygen pump and the fuel pump. So they're mechanically locked. They will always spin at the same RPM because they're literally on the same shaft. So that makes the start sequence for Merlin much easier and simpler than the start sequence for Raptor. In the case of Raptor, you've got an oxygen power head and a fuel power head, and they're different shafts, obviously, and you've got two turbines and two pre-burners. So, and they're cross-feeding one another. So the start sequence for Raptor is insanely complicated compared to the start sequence for Merlin.
It has to be perfectly precise because each one relies.
Basically, you're doing this delicate dance between the fuel power head and the oxygen power head, and if they get out of sync, then you can go stoichiometric in the pre-burners and melt or explode the pre-burners. So, starting an engine like this is very complex. Once it's running, it's a much easier situation. But that if you get anything wrong with that start sequence, you're either going to melt or explode the engine.
And I finally understand too. Once it's running and in a steady state, the advantage of full flow becomes pretty obvious. Just looking at the enthalpy and the mass flow through each turbine and the delta T, and I mean this just clicked like 2 weeks ago. I finally actually understood it as opposed to understanding it ish, but it clicks now and I fully appreciate it.
Yes. By the way, you have the wrong ISP for methane engines in your video. It's way too generous.
Which, the theoretical max ISP? Yeah,
that is not possible.
I don't know why.
I literally, I was just at a friend's house and they were watching the video. I'm like, I wish we could get ISP like that. That would be a dream. But it's maybe worth correcting. It's that's a way higher ISP than is actually physically possible. I wish it were possible, but it is not. But from an architectural standpoint, in order to approach the limit of physics of what is possible with maximizing the efficiency of a rocket engine, a high pressure full flow gas engine that's as good as it gets. There's not you'd have to figure out new physics to do better than that.
Right.
So the Raptor architecture is the highest efficiency known to physics.
Yep. Like you said one time, it's as if God himself had knitted the molecules together. You maybe get 1% better.
Yes, so we should be able to get 99% combustion efficiency, 99% of theoretical combustion efficiency, which is insane, basically. Literally, with divine intervention, you could do 1% better.
Right. And you're doing that
That's really saying something.
And you're doing that in such a short thrust chamber too. Like the actual chamber is so small.
Yeah.
Because is that because it's gas and it doesn't need as much time to fully react?
That's part of the reason. But also we actually have a whole bunch of injector elements. So when the gas enters the main chamber, it is already pre-mixed. It's like 90% pre-mixed. So you've got swill injectors, where you've got, again, this is sort of a class of injector element, is a swill injector.
Yep.
And so you've got oxygen-rich gas going down the center of, it's like a little straw, basically.
Yep.
So down the center of the straw, you've got oxygen-rich gas, and then coming in from the side of the straw with, there are a series of holes that are coming at an angle. So the fuel-rich gas is coming in sort of tangential to the diameter. So it's coming in
at the opposite direction.
Like oxygen's coming down the straw, and then fuel is coming in from the side from holes that are drilled such that you're going to swill the flow.
Yep.
And so that when that enters the main chamber, it is already, call it roughly 90% mixed. Okay. So the chamber is only doing the remaining 10% of the mixing. Yeah, more or less.
And so the actuators there are those hydroelectrical or what are those called?
No, so we're still using hydraulic actuators. They're just basically hydraulic pistons. What we want to move to down the road with the Raptor 3 or whatever we end up calling it would be electrical. Basically a screw drive, an electric motor with a screw drive.
Big servo.
It's a big servo motor. This is a like what you don't see here is that there's a whole hydraulic system on the vehicle side that itself is, there's a battery driving, electric motors driving hydraulic pumps into a reservoir that is then feeding the engine's hydraulic fluid. This is, when you look at total vehicle mass, this is not a good approach.
Right.
We just don't have time to put electric servo drives on the engine.
Right.
We'll do that, I don't know, in a few months. Now with Merlin, you've got a source of hydraulic fluid. So with Merlin, it makes sense to have hydraulic actuators because you've got a source of high pressure working fluid, because you use kerosene as a working fluid, and you tap off the fuel pump, take high pressure kerosene to drive the hydraulic actuators, and then the low pressure outlet of that, it goes back into the fuel tank.
Yeah.
So basically, it's a recirculating system with no losses, and it's a super easy move if you've got liquid kerosene. Since we have cryogens here, it is technically possible for us to use methane as a working fluid in the hydraulic actuators, but very scary.
Yeah.
Because the methane will want to gasify.
Right.
If you get gas bubbles in the hydraulic system, it's going to get spongy.
Yep.
And it's not going to work properly.
Yep.
So I did insist that we at least look at the comparison, but this was like the mass difference. There wasn't a huge mass gain for having a methane hydraulic system, and it was scaring the hell out of everyone, so me included. So it was like, I think we should just do it so that we aren't missing something important. But the smart move is going to be just have an electric servo.
Yeah.
Still needs like a lot of torque, because moving this engine fast is not easy.
And it moves so fast. Like when you see, the videos landing, I mean, it moves so fast.
Yeah. like a lot of the time it doesn't actually need to move that fast, but if you have, say, an engine out, then you've got to slew all the engines really fast to deal with an engine that went out. Yeah. So, the corner cases kind of drive the slew rate and the torque needed in the actuators.
And the total and the full angle too, right? The total gimbal.
Exactly. So if you get
degree.
it's basically like unexpected gusts or buffeting, wind shear, and engine out that drives the slew rate. You could move it a lot slower otherwise.
And then you even simplified what appears to be a ton of valves and things almost to that one box or some kind of, almost like you did with the was it called the octo valve in Teslas, where you unified all the valves into a single component. Is that kind of like what you did here almost?
Yeah, we combined a ton of parts into one. But now it's always better to delete things rather than optimize them, which sounds obvious, but possibly the single biggest mistake made by smart engineers is optimizing a thing that should not exist. That's why I've made it really mandatory to run through the first principles algorithm of first question the constraints and requirements, make them less dumb. Then step 2, delete the part or process step. If you're not adding back at least 10% of the things you're deleting, you're not deleting enough. And then the third thing is optimize. And then the fourth is, as it relates to production, accelerate rate. And then only the fifth thing is automate. And I've done it backwards many times. That's why I have to repeat this mantra to myself as well.
You wake up every morning, it's written in your mirror.
Yeah, seriously. And you need to do it recursively. So,
what's the one thing, when you look at this engine, what's the thing causing you stress? Is there a certain part or a certain thing that you're sitting there going, I'm not sure how we'll figure that one out?
Well, I mean, the single biggest thing I'd like to do with Raptor is to sort of delete more of the little fiddly bits, like the sort of the small pipes and wiring. Integrate, basically to delete and integrate a little bit more to get to the point where we do not need shrouds. So if we delete the shrouds, that's a dramatic reduction in mass and cost and complexity. But if there's any part of the engine that is susceptible to heat, then we cannot delete the shroud. Now we've made huge progress from Christmas tree over there to Raptor 1 Christmas tree. That obviously needs a shroud. It's got a zillion things on it. It would be impossible to protect all of that from being melted. On Raptor 2, we've made dramatic progress, but not yet enough progress such that we don't need a shroud. So the shroud would be for protection from heat and high aerodynamic force, like high Q. So, but we're not far. With a little more work, we should be able to simplify it enough to get to the point where no shroud is needed.
There probably still need to be one on the booster for re-entry since it comes in engines first. No?
No, that's neither ship nor booster should have a shroud.
Wow.
I'd like to. There's a lot of bolted interfaces that would be great to delete, because every bolted interface is. You've got basically heavy flanges, heavy bolts. You've got a seal, and you've got very high pressure, and you've got things ranging from cryogenic liquid to hot gas, and you've got ox-rich hot gas. So these are things that are very difficult to seal. So stopping a Raptor from at least from leaking is very hard.
Yeah.
It's gonna. Every interface there it has some leak rate that is above 0, and it's heavy and complex and everything. So moving to more welded interfaces would be a big improvement. I'd love to figure out how to, if we can get rid of throat foam cooling, that would get rid of a manifold and a bunch of interfaces as well.
Is that hopeful? Like, is that actually in the realm of possibilities, or?
It's possible. No, if you say like, if you give enough head-end foam cooling, you can get rid of throat foam cooling. The question is,
What's the trade-off?
Yeah, does that cause is it worth it? Do you lose so much in ISP that you're it's not, is it like no longer worth it, basically? Like it's the ISP penalty for head-end foam cooling could be so great that it's dumb, basically.
You know something I just realized like last week that I think the RD170 and RD180 does is they actually almost do like an expander cycle with a boost pump. So they actually take all the regen channels and use that to spin a boost pump before everything, just to kind of relieve a little bit of pressure on the head side, or on the inlet side. And I didn't realize that was an option, and it's a pretty cool, to almost in a sense combine cycle types like that a little bit,
Yeah. I mean, a boost pump is useful for reducing the ullage pressure or the inlet pressure to the engine.
Yeah.
So at high thrust levels, we need fairly high inlet pressure. As you reduce the thrust, you need less inlet pressure. So sort of a boost pump or like anything that's going to increase, like any kind of pump that's going to just increase the pressure, even a few bar going into the main pump inlets, is helpful for reducing how much ullage gas you need. So it's basically a mass reduction of ullage gas.
Yep. But you guys don't have your pump isn't that highly staged. It seems like your inducer and everything goes so, like, some pumps like the old SSME or the RS25s, hydrogen pump had like 4 stages to it or something. It just kept, increasing pressure. It seems like your guys' is so streamlined and simple.
I mean, I don't think of it as simple, but so
it's not.
Yeah. So take the aux pump up there. You've got a dedicated inducer. And the inducer is basically like a real flat propeller blade. So the liquid flow coming in is cut at a very shallow angle.
Yep.
So what you're trying to avoid is cavitation or bubble generation. If you start generating bubbles, the bubbles will actually eat away at your blades. Like, it's weird, like bubbles would chip away metal, but they will.
Really?
And if you cavitate too much, then you're going to just be a bubble generator, and you'll lose pressure. Starve the engine. Yeah. So, but even small amounts of cavitation or bubble generation, those bubbles hitting the metal. It's weird that a bubble could erode metal, but it does.
Is that more prevalent in the aux side than it is the fuel side, or is it prevalent in both?
It's prevalent. It happens in both, but there's like basically you've got the inlet pressure and the inlet temperature. So the colder your propellant is, and the higher the inlet pressure, the less likely you are to have cavitation.
Yep.
And then depending on how your inducer blades are designed, these are very rough approximations. But if you have like a shallow angle inducer, you're going to generate less of a wake than if you if say in the limit. As you increase blade angle, it stands to reason. Just like if you're churning your hand through water, you're going to create a wake. So a shallow inducer blade is less likely to create bubbles than this is a very rough generalization, but it's less likely to create bubbles or a wake than a shallow angle. So the inducer will cut the flow at a shallow angle, and so we've got an inducer that has a fairly small pressure rise that then feeds the first impeller, and the impeller is where you really have a huge pressure rise. So we've got an inducer, then 2 impellers, and that's what gets us to our pressure, to our sort of 7 to 800 bar on the oxygen side. And we want to actually make that higher over time. But it's a really nutty pressure. That's a very, very high pressure. Yeah. So it is crazy that you have such a pressure rise in such a short length.
Yeah. Yeah. This is an incredibly short length. I mean, it's
yeah. But and this is an inline power head. So I don't believe there's been any rocket engine flown that has an inline power head, but I could be mistaken. I do not believe there is one.
I haven't seen one either.
Yeah.
Yeah, that's a first for me. And that allows you to couple some of the forces too through the turbine assembly, right? Into the chamber and everything.
Yeah, we actually take the thrust load goes through the pump housing.
Yeah, yeah.
So you dual purpose the pump housing as the it serves as a pump housing and serves to transfer thrust load.
Yeah.
And it's a straight line situation, so you don't have any tube, you don't have any
like torques or anything like that.
Yeah, you don't have any there's no main, like for the fuel pump, which is off to the side, you've got a bunch of transfer tubes.
Right. Yep.
But for the aux side, you've got nothing.
It's all internal. It's all little internal channels.
It's just going straight down.
Yep. Okay.
Inlets coming through the gimbal to the inducer, through 2 impeller stages, and then and then it's feeding the turbine, oxide turbine, and the fuel side turbine. I'm like simplifying a lot of things, and I may have misspoken on a few. So forgive me if I've misspoken a few things, but this is about as simple as you can do it. Is have it the aux is coming straight through.
Yeah.
Essentially.
Yeah. Something interesting that I think it was like the RD701 or some obscure or 501 or something. I think it was the 501. It ran on fluorine or pentaborine.
Fluorine's insane.
Yeah, nasty stuff.
Don't use that.
They used some of the oxidizer for like cooling the chamber assembly, and they used the fuel for cooling the nozzle extension. Basically, I've never seen that. It seems maybe counterintuitive, or I don't know what the implications would be of trying to use liquid oxygen as a coolant. But I found it unique that they're daring enough to use both to actually do your cooling.
Yeah, I'm not sure what the point of using both would be, but yeah.
Other than, have you ever heard of a dual expander cycle, where you heat up both fuel and oxidizer? To me, the dual expander cycle is would be a really cool cycle type if you were to do an aerospike, because you can kind of exploit the additional heat, at the increased surface area of the throat, to be able to do, heat up enough gas to make the expander cycle a higher thrust option. Because I love that the expander cycle, the expander cycle kind of has a hard limit on, how much you can heat up the gas.
You start having surface to volume ratio issues.
Yep. But having a dual expander cycle, especially if you have an aerospike, it seems like to me that'd be a cool way to exploit the two, almost use the weakness of one for the strength of the other. But from what I know, no one's ever built one. There was a study on one in the 90s or something, but no one ever built a dual expander cycle aerospike, and that's my dream. I don't know why, I just love aerospikes. They just look so cool. I know I probably bring it up every time I ever talk to any engineer. I'm like, aerospikes. I just can't help it.
Yeah. If you have a 2-stage rocket, there's really not much point in an aerospike.
Yeah.
Because you just have a nozzle that's optimized for, more or less optimized for sea level, and have a nozzle that's optimized for vacuum, exactly. And you're done.
Oh, you know what so before Firefly became Firefly Aerospace, when they were Firefly Space Systems, they were working on an annular aerospike. The reason why, I was talking with Tom Marcusic about it, was because they're actually trying to be pressure fed for their booster, so that way they could keep a really short expansion ratio on the chambers. Since they don't have much tank pressure, they don't have much chamber pressure, they can do a really short expansion ratio and gain the rest of it out of a aerospike. That was their purpose for doing an aerospike on the first stage, was just to overcome the limitations of a pump-fed system to be able to be orbital. I thought that was pretty cool. I don't know.
I mean, you're going to have heavy tanks no matter how you cut it. So, I mean, in the entire history of SpaceX, we've only ever wanted to increase chamber pressure. You have never wanted to decrease it.
Yeah.
So.
That's a good way to put it.
Yeah.
Yeah, I'm sure there's never been a trade where you're like, what if we decrease the chamber pressure?
We've always wanted to increase chamber pressure, and we've never wanted to decrease it. We've always wanted to increase thrust, and we've never wanted to decrease it. You know, saying that too much thrust is like you're too good looking or something. I mean, it's just,
not something you're going to complain about.
Yeah. We've put a lot of effort into getting the chamber pressure to 300 bar. I mean, for those that are like really understand rocket engines, the thing that you'd want to look at is the chamber pressure plot. That's like the inside baseball thing that really matters.
Yeah.
And then there's like, they'll often like quote ISP, but actually the thing you really want to look at is area under the force time curve. So the point of the versus the mass flow. So you have mass flow,
yep.
like for a given amount of mass flow,
yep.
What is the area under the force time curve?
Area and force time curve.
Area under the force
area
versus time curve.
So
the point of the engine is to produce force.
Yeah.
When you're calculating ISP, you're making a bunch of simplifying assumptions.
Yeah.
And the ISP is actually not constant. So the ISP will fluctuate a little bit depending on mixture. Well, yeah, depending on what the ambient conditions, what the mixture ratio is, what throttle level you're at, but the thing that actually matters is the area under the force versus time curve. This is the thing you know, as opposed to an ISP approximation, especially for a vacuum engine, because you're not running the engines in vacuum, so you're making a lot of assumptions when you're calculating the ISP of a vacuum engine. But what you can measure very objectively is how much force did you produce. So you have like time,
yep.
and then force, and what's the area under the force versus time curve.
Okay.
Because that's what the purpose of the engine actually is. ISP is an approximation of that.
We need a cool, sexy name for that. For, you know, ISP.
Integrated force.
Oh,
what?
That's not that fun. We need a sexier name for it. Like specific impulse is pretty catchy. So.
Yeah.
Yeah.
May the force be with you. How much force do you know? This is a force generator.
Yeah.
So.
The force field plot.
Yeah.
Should we?
Yeah. So anyway, this you can see basically a lot of improvements and more to come. And a big move will be when we can not have shrouds.
Yeah.
So.
Are you hoping to be able to fire this thing off? Do a static fire of booster pretty soon? I assume all these are going to go on booster 7.
Yeah, these are meant for booster 7. So, yeah.
That's going to be the craziest thing to see when you get 33 of these things roaring. I mean, that's going to be, that will be utterly ridiculous.
Yeah, we had a slight issue with the Booster 7 test where we collapsed part of the LUX transfer tube. So we're going to go in and repair the LUX transfer tube that collapsed. So that will probably take us a week to fix.
Yeah. And something new to the, is it new to B7?
Hello.
Just, good. Just hanging out, talking rockets.
I was just mentioning we had the LUX transfer tube collapse, which we've got to go in and repair. It might take us a week or so.
Yeah. Well, great lesson learned, but we always get into tests and learn from it. And
yeah. So.
that's why Starship is awesome.
Yeah. Rapid iteration.
Yeah. So I don't know what we should do.
Should we go up and
Yeah, we can look at the high bay and stuff.
yeah, let's do that.
Thanks, Elon, for being so generous with your time. And also thank you, Ryan Chalinsky from Cosmic Perspective, for helping to capture this awesome conversation. And I owe a huge thank you to my Patreon supporters for helping make content like this and everything we do here at Everyday Astronaut possible. If you want to help me continue to do what I do, head on over to patreon.com/everydayastronaut. And while you're online, be sure and check out our awesome merch shop where you can find shirts like this and lots of other really cool stuff like our long-awaited dress wear, our new tiny human shirts, or our 1/100 scale Falcon 9 model rockets, well, when they get back in stock. Find it all at everydayastronaut.com/shop. Thanks, everybody. That's going to do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.